How's it going, everybody? Let's do some dimensional analysis. What I have here is we have a sample of rubidium phosphide. I just picked some crazy number, 11.406. Just pick some numbers. So before I do this, though, I want you to pause this video and for rubidium phosphide right here, okay? For this substance right here, see what you can remember and see if you can do this on your own. So I'm going to go ahead, pause your video right now, and then, so I'm going to put a little pause in this video for about a couple of seconds. That'll give you an opportunity to just press pause, practice on your own, and then you can unpause it. All right, and then pick up where I begin the lesson again. All right, so go ahead and pause now if you'd like to practice on your own. All right, so now we're back. So hopefully when you did this, you remembered that rubidium has a +1 charge, and that phosphide means phosphorus, and so you were dealing, wow, that's pretty bad. So you were dealing with a -3 charge. So knowing that, so this charge here is basically a +1, right? And this is a -3. Well, you need it to equal 0. So that means you would need 3 of these, because 3 times 1 is +1, right? So, or 3 times 1 is +3, sorry. +3 plus -3 would give you 0, check. So we would need 3 of these and 1 of these, right? So hopefully you remember that you should have Rb3P. That should be the formula that you have for rubidium phosphide. Okay? All right, so number 1, how many moles are in the sample? So let's take a look at this. Number 1, how many moles are in the sample? Always start with what you're given, which is basically the mass of it, and then the actual substance itself. So we've got 11.406 grams of the rubidium phosphide. That kind of looks like a 4, doesn't it? There we go, that's better. All right, so now remember, let's see, let me see if I can draw these lines here. Let me move this over. Maybe this will help if I put it over here to the side a little bit. All right. So remember, it's about getting rid of units. So we're gonna, this entire unit, grams of whatever substance is there, that entire thing is the unit, not just grams. You have to include the entire thing. So we're gonna basically need grams of rubidium phosphide, right? And so we go to our, so you go to your periodic table that you've got, right? And so from your periodic table, typically for what we have, the tools that we have are what's that number that we call it? You know how you have your uncertainty? So typically the tools that we're using in the lab, they have an uncertainty value where you make your estimated digit in the 100th place. So for that reason, a lot of the problems that we do, what we're going to do is take the numbers from the periodic table round it to the nearest 100th to account for that uncertainty that we have in lab. And so we'll already be rolling that into our answer. And so that's what I'll expect you to do. So for instance, rubidium, all right, if you look at rubidium on the periodic table, 85.468, so 85.47 is what you should be using. And then phosphorus, 30.974, so you should be using 30.97 because that 4 will not round up to 7, right? All right, so now pause this video, take a moment, see what you come up with for the molar mass for rubidium phosphide. All right, hopefully you got the same thing I got. So when I calculated everything out, 3 rubidiums and 1 phosphorus. What I got was a total of 287.38 grams. I got 287.38 grams per 1 mole of this particular substance. Okay, and then remember, like units on bottom and top, cross them out. Get rid of them. Just don't leave it there. It has to go away. Just like math class. X over X cancels out. Y over Y cancels out. Donut over donut cancels out. All right. 50 over 50 cancels out. That's a pretty straight line. All right, so now at this point right here, number 1 is asking us for moles. We don't have to do anything more, so I can come over here. I just started putting down more stuff because I'm used to doing longer problems. We're done. So moles rubidium phosphide. Number 1 says how many moles of the substance do we have? We're done. When the only unit that's not canceled out is the one that you're solving for, multiply all your fractions together. So you have 11.406. Okay, 11.406. I'm going to divide that by 287.38. And then what we get is 0.0401083306. We got a lot of numbers. All right, so that just gives us moles of this particular substance, the rubidium phosphide. And so what we want to know is what's the best final answer? You just don't write everything in the calculator. Sometimes the calculator gives you way more numbers than you need, and sometimes it gives you not enough numbers. Sometimes you actually have to add numbers to what is there, and hopefully you remember that with your significant digit rules. Okay, so right here, this is 1, 2, 3, 4, that's 5 significant digits, okay? 11.406, that's 5 sig figs. So the first sig fig is here, so there's your first one. 2, 3, 4, 5. So there's 5 significant digits. This 3 is not significantly high enough in value to make it seem like we're close to this being a 9. So think about it this way. 83 is closer to 80 than it is to 90. So right here we would just keep this 8. So the good final answer for this one is 0.040108 moles rubidium phosphide. Number 1 is done. So if you have any questions about that, pause and go back and re-listen to this video if you need to. All right. And we'll have plenty of examples to go by. So let's take a look. Let's look at number 2. What's 2 asking us? The mass of phosphorus atoms that are in the sample. Okay, so the first thing you should remember is whatever number you get, law of conservation of mass, phosphorus is a portion of all of this. Of course I'm drinking coffee. So you should see that the phosphorus is a portion of this entire compound. So think about this. If you had 1 molecule rubidium phosphide, you've got 4 atoms there. If you just had 1 molecule, you have 4 atoms there. And one of those atoms is phosphorus. 3 of those atoms are rubidium. But those atoms don't have the same mass. So the mass is not proportional as far as just because you have 4 of them, it's 1/4 of it. It's a different fraction. It is a fraction of the whole. It's a portion of it. But if we were to add up the mass of all the phosphorus and all the rubidium atoms, no matter what our sample size, it has to equal the sample size, right? So we know that looking at this, rubidium, remember, has a mass of 85.47, and there's 3 of those. So the majority of the mass right here is rubidium. Phosphorus, remember, it is 30.97, so a smaller portion, a smaller ratio, a smaller fraction is phosphorus. So keeping that in mind, when you're done, you realize that you should have a number that is definitely less than 11.406, and it should be a small portion of that number, since the phosphorus, since 30.97 is a small portion of that overall sample, no matter what your sample size is, right? So let's get started. So let me move this up a little bit for us. All right. So we've got 11.406, and that is grams of rubidium phosphide. All right. So we already know the molar mass here, right? We already know that we've got 287.38 grams of rubidium phosphide, right? For every 1 mole. So we know it's molar mass, right? And remember, we've got to take care of business. Cancel out units. All right. So now at this point, what we want to know is, what is it we're trying to figure out here again? How many phosphorus atoms are there? All right. So what you have to do, obviously, is bring this down here. So 1 mole rubidium phosphide. So let's think about this. Let's think about what we know about ratios. This is a mole of substance, which means that there's 1 mole of this whole thing here. And in that ratio, in 1 mole of this, there's 3 moles of rubidium and 1 mole of phosphorus in this sample. And so in number 2, since we want to focus on the phosphorus atoms, basically we're going to separate out the phosphorus atoms in this. So if we had 1 mole of this substance, there would, because of the ratio of atoms that are there would have to be 1 mole of phosphorus atoms in that sample. Okay. So now cross out like units again. All right. I like using different colors when I can. Just helps with the housekeeping stuff, right? So now right here we got 1 mole of phosphorus atoms. Got to bring that down to the bottom, right? You got to cancel out what you don't want. So there's 1 mole of phosphorus atoms. And in 1 mole of phosphorus atoms, how much mass would you have? Well, go back to your periodic table, and we know that if we had just 1 atom of it, of one atom of phosphorus, we'd have 30.97 atomic mass units, AMUs. But if we're talking about a mole, that means we have Avogadro's number of it. That's 6.02 times 10 to the 23rd. That's a lot, but the ratio is still the same. So that means that we would have to have that many grams of it. So that means we have to have 30.97 grams of phosphorus atoms, right? Cancel out our like units, moles of phosphorus atoms, moles of phosphorus atoms. So we want grams of phosphorus atoms, so we're done. So we just multiply these 4 fractions together, right? So if we multiply these 4 fractions together, so we've got 30.97 times 11.406. We're going to divide that by the 287.38. You should see that you get 1.22918. We just need some extra numbers. So we know going back to here that we've got 5 sig figs there. So let's kind of see 1, 2, 3, 4, 5. 5 takes us right here. So with the 87, we have more than enough numbers. There's extra numbers in there, right? You should have something like maybe a 209, right? And then, of course, that would be grams of phosphorus atoms. So 1, 2, 3, 4, 5 sig figs. That 8's going to round that up. So that's going to give us 1.2292 grams of phosphorus atoms. And we've got ourselves an answer, ladies and gentlemen. And let's think about this. Before we did the math, we looked at the sample we had. We looked at the mass of rubidium and phosphorus, and we saw that the majority of the mass of the substance itself, no matter what your sample size, 11 grams, 2 grams, 5 million grams, it doesn't matter. The majority of it was rubidium, and the smaller portion, which means ratio, is phosphorus. And so we see we've got 1.2 out of 11.4, essentially. So our math is looking pretty good, all right? Um, so let's look at this. Let's I so one thing that I found that people do is where they'll get some stuff wrong is they will start with this number here. So let's just say instead of starting with the mass of it, they would start with moles of. So let's do this. Let's take what's here we converted grams to moles, right? Which is basically this part right here. So if we didn't do the rest of this right here, all of this is the same. These two fractions together is that number. So I know that I've noticed in the past a lot of people would take this number and start with that one to do their math, and then wonder why that in lab something isn't working right, okay, or on a quiz or a test, why they're losing points. So let's take a look at that. Let's start. We got 0. What was that? 0.40108, and that was moles rubidium phosphide. What I'm doing here is I'm showing you why you should always start with your original values and not with some other calculated value that you have, okay? Because here we're gonna see where error is introduced. Okay, so we have to bring this down here, right? We have to bring that unit down. Moles of rubidium phosphide. All right, so if we went moles of rubidium phosphide, how many moles of phosphorus do we have? All right, well, in 1 mole of this substance, there would be 1 mole of phosphorus. That looks pretty straightforward, right? Let's cancel out that unit. All right, so if we had 1 mole of phosphorus, how much mass would we have? When we look at our periodic table, we see, remember, it's 30.97, right? All right. So and we can put atoms here if you want. So let's multiply this right here. So if we multiply this, we get 30.97 times 0.040108. All right. I punched in a wrong number by accident. I knew that looked a little weird. So 30.97. I had 30.7 times 0.040108. All right, that looks better. That gives us 1.242.144. So 1, 2, 3, 4, 5. So there's the 5th number right there. That 4, not significantly high enough to round it up to a 2. So right here we would go 1.2421. Well, so we look at this and we go 1.229, 1.242. Well, they're both 1.2, but this one is 1.24, 1.22. Is that a significant difference? Well, let's see. Let's find out. Grams of phosphorus atoms. Let's find out. So the only way to find out would be for us to go back to the original value and to figure out the mass of rubidium in this 11.406 gram sample to find out if those two numbers, even though they're very close, if one of them is just too high, it's just not appropriate, right? So let's figure out the mass of the rubidium in this sample. This is how we can check our work. 11.406 grams of rubidium phosphide. Okay, so remember we said there's, oh, that's pretty bad, 287.38, right? Yeah, 287 grams of rubidium phosphide in 1 mole of rubidium phosphide. Let's cancel that out. All right, so in 1 mole of this, we know we have, what are we trying to figure out? 3 moles. We got 3 moles rubidium. Right here, you can see that. There's not, that subscript there means there's 3 moles. There's a ratio of 3 of these for 1 of these. So to have one mole of this whole substance, you have to have 3 times the number of phosphorus, right? Okay. And then 1 mole of rubidium, we said, is 85.47 grams. All right, so let's cancel out our units that cancel out. All right, so now let's see here what we got. 85.47 times 3 times 11.406. Divide that by 287.38. 287.38. You get, drum roll, you get, what was it, 10.176812 grams of rubidium. So now let's look at this. 5 significant digits, right? 1, 2, 3, 4, 5. So that 8 would round that up because there's 1, 2, 3, 4, 5. So we get 10.177 grams of rubidium. All right, so let's think about this for a second. Up here, so the total mass is 11.406. So with this first one that we calculated out right here, we had 1.22, what was it? 2292 grams, and down here we have 10.177 grams, right? So 1.2292 plus 10.177, you should see that if we add both of these together, we get 11.406 and then a 2. Well, where did that extra 2 come from? It came from that right there. If you think about this, well, all we did was just line up the same number of units. When you add numbers, you're looking to try to get the correct number of decimal places, right? Well, we can get rid of that since we got rid of it over there, right? 11.406. That's our math. Well, you should very easily be able to see that if we had grabbed 1.242 from this up here, right? Because that one's not going to round that up, and then all of a sudden we have 10.177. All right, so we get 1.242 plus 10.177. All right, and of course that's grams and that's grams. Add all that up together, we get 11.419 grams. So the question is this: is the difference between those two numbers? You got 19. If you had 19 and you had 6, that's 13. So if you're talking about pennies, 13 cents is not much. But when we're talking about grams of substance right here, I mean, that's a significantly different number. So that is significantly higher. Well, so let's think about this. What did we do that did this, right? So if you look at this number right here, this is a rounded figure. All these other numbers are actually a part of that value, but we just dropped them. We got rid of it, which means we effectively rounded this up. We dropped this 306 right here, and there's more numbers after that. And so we're using a rounded figure, which introduces that error from the get-go. So remember, you should only round one time, and that's at the very end after you've done all your calculations, after you've accounted for all your significant digits, and you've accounted for all of your uncertainty, which means use your original values and carry over those extra numbers until the very end, round one time at the very end. When you do, law of conservation, all those numbers should equal 100% of everything you've got, both reactants, products, the total amount of substance you started, total amount of substance you have at the end of the calculation. Doesn't matter, right? So all I did here was just prove to you number 2, I wanted to prove to you that it would be a bad idea to start with this number to try to figure out number 2. Always go back to the original values, start with the original values. Okay? All right, so now number 3. I'm going to pause for a second, give you a chance to rewind that section if you need to, in case that didn't make any sense to you, and you just need to hear it again. Okay, we're back. All right, so number 3, the total number of atoms in the sample. Again, so I've already proven to you why we need to start with the, where's my cursor? There it is. I've already proven to you why we need to start with the 11.406 grams of rubidium phosphide. So of course, we bring down the 287.38 grams rubidium phosphide. We know that that's in 1 mole of this substance. So remember, this whole fraction here is molar mass, right? Let's get rid of that unit. Oops. I'm just trying to be consistent with my colors for you. All right, so what are we trying to figure out in this one? Total number of atoms. Total number of atoms. We've got a mole. We've got a lot right here. We've got a whole bunch of stuff here, right? So we figured out up top that we only had like a fraction of 1 mole. So if we're dealing with moles, remember we're dealing with Avogadro's number when we're counting parts. And this thing is asking how many atoms total do we have? So if you're looking at 11.5 grams, you're looking at a lot of atoms, right? So bring this down here. So 1 mole of rubidium phosphide, 1 mole of anything has Avogadro's number. 6.02 times 10 to the 23rd. In this case, it would be molecules of the substance we're working with, which is rubidium phosphide. Okay. Remember, a mole of humans, 6.02 times 10 to the 23rd humans. A mole of donuts, 6.02 times 10 to the 23rd donuts. Doesn't matter. All right. The unit we have is molecules, so we're just counting molecules. Now, in 1 molecule of rubidium phosphide, how many atoms do we have? Well, if we were holding 1 molecule of it, 3 rubidiums, 1 phosphorus, that's a total of 4 atoms. All right, so get rid of our like units. All right, it's about canceling out units. Cancel out units. Cancel out units. I cannot stress that enough. You have to cancel out units, right? So let's see. Let me go ahead and I'm going to let's see. I'm just going to shrink this down just so I can keep it all on one page for you. All right. So yeah, let's multiply all this stuff right here. So If you're using like a TI-84 or one of those better scientific calculators, they'll have the EE button on it. If you're using something like these right here, this is really all you need to do this type of stuff. You don't need anything fancy. You just need something to do this. All right. There will be, if you find where the 8 button is at, if you go 3 above it, you'll see something that says times 10 with an N on it. You'll see a little button that says times 10 with an N on it. That button right there also works as your scientific notation button. So let's get rid of that. So what we've got, so I recommend you putting in scientific notation first, pressing enter, puts it into the memory, and then you'll run across less errors with what you do, right? So 6.02 times 10 to the, now press 23rd and enter, and you should see that you should have that value in your calculator, probably with like a little caret and then a 23 after it. Or if you're using a more advanced calculator, it'll have EE with the number on it. It means times 10. All right. So now what do we have? Times, what is that? Times 4 times 11.406. Remember, we're just multiplying all our numerators, right? So you should get 2.7465. There's a bunch of numbers times 10 to the 25th. Okay. And that makes sense if you think about it. You took something that was you took 6 times 11 times 4. And remember, scientific notation, you typically move all of your you move your decimal over into, it just is in front of, there's only one number in front of it. So the calculator is already programmed. It usually defaults to just moving it so that there's only one number in front of the decimal. So it adds those in. Remember, when you multiply exponents, you add them. Right? Divide, you subtract them. All right, so now we're going to divide this number here by 287.38. You should see, oops, you should see 9.5. What was that, 5? Let me do that again. I think I put some, 6. Oh, I pressed 3. 6.02 times 10 to the 23rd. What's that? Times 4 times 11.406 divided by 287.38. Yeah, there we go. 9.557257. And when we're done, we need what? 5 significant digits. 1, 2, 3, 4, 5. So the 5th one is here. We could stop right there. And this 57, there's an argument that says, in this case, the 5 would round it up. An argument that says that it wouldn't. 57 is closer to 60. So we could say that, yeah, let's just go with the standard that it's going to round it up, right? And of course, this is times 10 to the 22nd, right? And that would be atoms. All right, so now, so we go with 9.5573 times 10 to the 22nd atoms total. That's the total number of atoms that we got in this thing. So that's it. That was the total number. So if we had to figure out the total number of rubidium atoms and the total number of phosphorus atoms, when we get those two numbers and we add them together, they have to equal 9.5573 times 10 to the 22nd. They have to. So we already know that if we were to do the math to figure out how many atoms of phosphorus, it would have to be a smaller fraction of the 9.55, and that the rubidium would be the larger fraction of the 9.55. But they both have to add up to 9.55, right? So both the answers would be 9.55 times, or would be times 10 to the 22nd, right? You add them all up, and we would get the total number of atoms. So I'm hoping that helped. So yeah, you'll have some practice problems that you can work on. I'll do another one of these videos with a different substance, kind of coming from a different angle, but essentially kind of doing all the same thing. All right. Hope this helped, and oops, you have a good one.